This course is EE 205N, Signals and Systems, and this is lecture 1, in which we will try to introduce the course and some of the basic concepts associated with signals and systems, which we shall often abbreviate as S and S. My name is this. I'm a Bengali and I would like to be pronounced as Dutta Rai. Our main text is Signals and Systems by A.V. Oppenheim, A.S. Wilsky and I.T. Young, and we shall abbreviate this as OWY. This is a Prentice Hall publication, 1983. For most of the course, except the last topic, we shall use OWY. For the last topic, which is signals and systems of a very special kind, namely random. For random signals and systems, we shall use Methods of Signal and System Analysis by G.R. Cooper and C.D. McGillen. This is a 1967 publication, Holt, Reinhardt and Winston. You need not purchase this book. If necessary, we shall give you handouts. Now about the topics that we shall talk about in this course. Firstly, we'll introduce the topic of signals, systems, basic concepts and so on. We shall show how to characterize signals and also how to characterize systems. We'll talk about various kinds of systems, and then we'll talk about a special kind of systems in much more details. This is linear time invariant systems. This is the abbreviation LTI. Under this, we will talk about their properties and response, and we shall introduce a very useful tool, namely convolution. Then we will go to Fourier analysis for continuous time signals and systems. We will try to tell you who Fourier was and why Fourier analysis is so important. And then we shall do the same for discrete time signals and systems. These are highly mathematical topics, but we will point out how they are utilized for engineering systems, in particular electrical and computer engineering. We'll look at how discrete signals are produced. We'll look at how sampling is done of a continuous time signal to create a discrete time signal, its limitations and so on. And then we shall go over to the Laplace transform. We will introduce the basic definitions and we will talk about its properties and how Laplace transforms are used in practical system analysis. What is Laplace transform for continuous time systems is achieved by the so-called Z transforms for discrete time systems, and we shall look at the Z transform and its applications in characterization of discrete time signals and systems. And finally, as I told you, we shall talk about signals which are not deterministic, which are random, and many signals in practice are indeed random. And if there is a random signal, how does a system respond to such a random signal, and how do we characterize such systems in practice? This in brief shall be our aim in this course, and we hope to complete these topics in about 40 odd lectures. We next ask the question, what are signals and systems. You see, the complete field of engineering, and in fact any activity of human being, can be thought of as an interaction or interplay between signals and systems. Systems can be of various types. They can be physical systems, they can be biological systems, but whatever the system is, system, if we represent a system by a block, then the definition of a system is that it is a meaningful interconnection of physical devices and components, a meaningful interconnection. For example, if this chair is put upside down and a person is standing at the corner of this room, this does not form a system, because the chair is meant for sitting of a person and it must be put in a position so that the person can sit. And if the chair is there and is not coupled to the person who is going to sit, well, it does not make a meaningful interconnection. You can at the most call it an assembly of physical devices. It is not a system. A system is a meaningful interconnection of physical devices and components. If a system is broken up into various parts, each part is called a subsystem, and therefore you can also say a system is an interconnection of subsystems. Subsystem in turn is composed of physical devices and components. A system by itself cannot achieve anything. A system must be closely interlinked to what? To signals, to quantities, or to phenomenon known as signal. A signal in general is a dependent variable. A signal in general is a function of one or more independent variables. For example, you could have a signal which is a dependent variable depending on n number of independent variables, x1, x2, xn. It is extremely important that you understand that a signal is a variable, a constant quantity like a battery voltage, or let's say if the salary of a person, for example, from month to month remains a constant, it does not give any signal. It doesn't say anything about the type of work that the person is doing, for example. A constant is a boring phenomenon as far as engineering processing is concerned. A signal must be a variable, and mathematical characterization is in terms of a function. If the signal is a function of several variables, then it is called a multivariable function. If it is of a single variable, like you have a function x, let's say, of a variable t being the usual time independent variable, then you say it's a single variable function. And therefore a system must receive a signal, and then what the system does is it processes this signal and produces, in order that a system be useful, it must produce another signal which in some respect is more desirable than the original signal. This is the purpose of signals and systems, and therefore, well, you understand that the output signal is another function g of same variables, that is x1 to xn. If this broad concept of a signal is taken into account, then you see that all engineering phenomena, in fact all phenomena in the world, living or non-living, can be characterized in terms of this broad visualization. That is, we have system or systems, and we have signals which these systems receive, they process, and then produce another signal which in some ways is more desirable. For example, an electric motor. Well, it is a system. By itself, if the motor stands in the laboratory on the floor, it is a useless system. It becomes useful only when excited with a supply, and then it rotates and performs mechanical work, and therefore electrical voltage is its input signal and its output is mechanical work, and therefore we can characterize a system like this. Now, a very common system that you have already been familiar with is an electric circuit. Electric circuit, for example, a simple RC circuit, let's say like this. Well, this is a system. It receives an input. Let's say you apply a voltage source here, VIT. This is the functional form. VI is the function and T is the independent variable, a function of time. This is a signal called the input signal, and then you produce from this an output signal which could also be a voltage V0 of T. The functional form is different, that's why V0 is different from VI, and this is a very simple example of a signal and system interaction to produce something useful. For example, you know that this RC circuit is an integrator, and therefore if you put here a waveform like this, if your VIT is like this, then what it shall produce is a linearly going ramp. All right. So this is an example of a system and its interaction with signals to produce something useful. Let's take another example, a non-trivial one. Suppose you have a PC in which there is embedded a computer program to diagnose, to analyze and diagnose ECG recordings, to analyze ECG recordings and diagnose if there is any defect, a computer program. Now what you feed to it is an ECG record, electrocardiogram record, and the PC, the program, then analyzes this record and detects or gives out an output signal which could be the heart condition of the patient. This is a heart monitoring system. You take an ECG, it could be an online processing. You take an ECG, it is automatically analyzed by the system, and then at the output, let's say there can be a printout or it can be on the monitor that the heart is weak or it needs a bypass operation or something. This is a physical system. As another example of systems and signals. And in general, let me say we are not overemphasizing by saying that every activity, every human activity can be characterized in terms of an interplay or interaction between a signal and a system. Now, in signals and systems, or in engineering in general, there are two kinds of problems, basically. One is that the system is given, the input signal is given, this is given, and you have to find out the output. So we say, if this is given, the system is given, and you have to find out the output, this is one kind of problem. This is the usual, most of the problems that you shall study during this course or during your stay in IIT would be such problems. But there are another class of problems which are also very important, which we shall come to in a minute. But this problem is known as the problem of analysis. Okay, that is, the system is given, the input signal is given, you are required to find out its response. This is the usual thing that occurs in life. The systems, actual biological systems, the systems are known. How does it respond to a stimulus? This is the analysis problem. On the other hand, if the input is given and the output is given, that is, I have a certain kind of an input signal and I want to produce another kind of signal which is more desirable, what should be the system? This is a much tougher problem, and this problem is known as the problem of synthesis or design. Synthesis or design. This, as I said, is a tougher problem than the analysis problem. Synthesis is always tougher than analysis. And the other distinction is that to an analysis problem, a solution always exists. The problem may be difficult, solution may be difficult to find. You might have to spend 2 hours on the computer to find a solution. But to a synthesis problem, the solution may or may not exist, because what you are asking for may be something impossible to achieve. This differentiation should be understood. Difference between the analysis and synthesis aspects of system problem. In this course, we shall mainly deal with analysis. Not quite analysis. We will talk about analysis tools. That is, how do you analyze? How do you characterize, first of all, a system mathematically? How do you characterize a signal mathematically? And if the signal is given and the system is given, how to compute its response? It depends on what kind of system it is. It depends on what kind of signal it is. And therefore, basically the purpose of this course is to expose you to some of the important analysis tools for engineering systems. The importance of this course is that it is one of the foundation courses for engineers of all varieties, not necessarily electrical and computer, but all engineers need to know this. In the electrical engineering and computer engineering departments, we recognize this as a separate course, whereas in other engineering, perhaps they do it throughout their curriculum at various places and so on. We have collected them all together for one purpose, namely that if you are equipped with these tools, then when you go to courses like circuit theory, control engineering, communication systems, you will feel very comfortable because the basic tools are known to you. The Fourier transform, Laplace transform, Z transform and so on. And these courses and a variety of others, for example, neural networks, robotics, and name it. All the other courses that you shall be exposed to in future years shall have their foundation tools in this course, and therefore it is extremely important that you understand these tools, you absorb these tools and be able to apply these tools. This is the sure test that you have learnt the material carefully. Now we talk about in this course basically of one type of signal, namely those which depend on the single variable, namely time. And a signal shall be denoted by this symbol small x. It is extremely important to distinguish between small x and capital X, which we shall come later. Small x of t, small x is the dependent variable and t is the independent variable. We shall also come across signals which are x of not t but of an integer n. And basically the distinction is that this is a continuous time signal and the other one is a discrete time signal. Let me explain what we mean by these terms, continuous time and discrete time. Suppose we have a signal like this, a plot of x of t versus t, and let's say my signal is this, some amplitude a, then it falls down linearly on both sides and it reaches 0 at some point here and at some point here. Alright. Now this signal x of t exists or is defined at every value of t, that is over a continuum of t from minus infinity to plus infinity. At every value of t, x of t is defined and is known. Such a signal is called a continuous time signal. Alright. On the other hand, if I have a signal in which only these values are known, values at discrete instants of time, that is, let's say t1, t2, t3, t4, then t5 and so on. Similarly, t minus 1, t minus 2 and so on. And at t0, okay, if this signal is known at only these discrete instants of time, their amplitudes are known. Between t1 and t2, the signal is not defined. It does not exist. Such a signal is called a discrete time signal because it exists only at discrete values of time. It does not exist anywhere in between. Alright, is the concept clear? This interval, that is the difference between t1 and t0, the difference between t2 and t1, the difference between t3 and t2 need not necessarily be uniform. If it is uniform, that is, if t2 minus t1 is equal to tn plus 1 minus tn for all n, if this is true, then we say it is uniformly sampled. It is as if there is a continuous time signal which you have sampled at these discrete instants of time. On the other hand, if these intervals are unequal, that is t1, t2, t3, t4, these are arbitrary, then we will call it a non-uniformly sampled signal. Alright, so you understand the difference between continuous time and discrete time signal. I must say a word about the notation of a discrete time signal. as far as continuous time is concerned, there is no confusion. X is the signal, the dependent variable, and t is the independent variable on which x depends. On the other hand, in the discrete time signal representation, the time does not figure at all. Small n stands for an integer variable. And how this occurs is like this. Suppose we take the same signal again. And let's say we sample uniformly. That is, we have 3 here and let's say 3 here. And uniformly, all right. And let this interval be capital T. Therefore, this will be 0, this will be 0, this is capital T, this is 2t, this is 3t, and so on. All right. In most of the discrete time signals that we shall talk about in this course, we shall consider uniform samples. That is, uniformly spaced samples. This spacing is in time. And in the description of this signal, what we should actually specify is the value of the signal at n times capital T, where n goes from minus infinity to plus infinity, but is an integer. All right. What we do for brevity is, if this is uniformly sampled, then we cut out this capital T from the notation. That is, when you write x of n, it actually means x of nt. N is an integer. So a discrete time signal you shall always denote by x of an integer variable, and these symbols are reserved, usually reserved for integer variables. That is, I, instead of x of n, I can have x of I, j, even though j shall also be used for square root of minus 1, but in the context there shall be no confusion. If we write x of j, it means that j is an integer variable, ij, then k, L sometimes is used, M of course is used, N, not O, then sometimes P also is not used, Q is also not used, R, and that's it. These symbols I, J, K, L, M and R are usually used for integer variables, and if one writes x of k, it will immediately mean that it is a discrete time signal sampled at the instant k times some specific interval capital T. All right. Capital T in that context is called the period. We will come to this later. Another way of looking at this is that capital T, the sampling interval, is normalized to unity. If capital T is 1, then obviously nt is equal to n. So there are both ways of looking at this strategy. I shall close this lecture by saying, why should we consider discrete time at all? Why should we consider discrete time systems or signals at all? Whereas all phenomena in the physical world is continuous. Time is continuous. What else? The flow of river is continuous. A process, chemical process is continuous. Why should we consider discrete instance of time? The reason is that most continuous systems can be analyzed or processed or looked upon more comfortably with discretization, because of the revolution in integrated circuit technology. Things have become possible now to look at discrete time signals and their treatment by systems more comfortably, more accurately, more reliably by a computer, digital computer. And this is why discrete time systems have become extremely important. Discrete time systems, it is not that they do not occur in nature. They do occur in nature. For example, if you want, let's say, the national economic data for planning, then what do? You record GNP, let's say, year-wise, 1989, 1990, 1991. Now, year-wise means 1 year is capital T. Is that clear? 1 year is capital T. Or let's say you want to record the flood situation in Bihar, let's say. Then you set up some of the gauges, and the gauges are not read continuously. It's not that you cannot record continuously, yes you can, but they are very crude things. They are pillars with markings. You must have seen when crossing a railway bridge, there are pillars like this with markings. And what one does is, let's say every month, a reader goes there and reads the reading, records it. Then he sends it to a central mechanism for processing this data to be able to forecast what will happen next year, or to link it with what happened in the previous year, so that appropriate flood control mechanisms can be set up. We will close here, and in the next lecture we will give formal definitions of signals, systems and their characterization. Thank you.